Alright class, so we're going to start a new chapter, thermodynamics. And this is the chapter that people usually like it in Chem 1B because it has a lot of things from Chem 1A. Now, thermodynamic. If you remember back in Chem 1A, we said that when you have a reaction, the reaction could release or require energy, right? And when it releases, so we could release or require energy. When it releases energy, what do we call that? We call that exothermic reaction. And if it requires energy, we call it an endothermic reaction. Okay. Now, let's give you an example. Calcium carbonate over time can decompose to calcium oxide plus carbon dioxide gas. Delta H of this reaction is 178.1 kilojoules. Okay. Now, what does this mean? I give you a delta H of a reaction is positive 178.1 kilojoules. Now here's what you need to remember. When the delta H is positive, the reaction is endothermic. That means it requires energy. If a delta H is negative, the reaction is exothermic. That means it will release energy. So this is key. So here's the reaction. My reaction is endothermic. Now, if I have a beaker and this reaction is going on, what does this mean? So if right now I had a beaker and this reaction was going on in a beaker, would my beaker get hot or would it get cold? I'm talking about this reaction. Let's say we're able to do this reaction in a beaker. Would the beaker get hot or get cold? What do you think? So we said positive delta H means endothermic reaction. When you are in endothermic reaction, you need energy. What are you going to do? You're going to grab the energy from your surrounding. If you grab the energy from your surrounding, what's going to happen to your surrounding? Your surrounding is going to get cold. Your surrounding is going to get cold because you're getting the energy from your surrounding. Now, on the other hand, if I had an exothermic reaction, that means you're releasing energy to the surrounding. If you release to the surrounding, that means my beaker is going to get hot. Okay? Another fun example. When you drove your car, I was going to say when you drove your car to class today. Alright, so you cannot drive it right now. You have to be at home. But when you used to drive your car to class, is that an exothermic reaction or endothermic? What do you think? It's an exothermic reaction because when you drive your car, after you drive your car, if you go and put your hand on an engine, do not do that. But if you kind of like feel the engine, put your hand above the engine, you're going to see that engine is hot. Because driving your car, exothermic reaction, release energy to the surrounding. Okay. Now, how about glow stick? Have you guys had glow stick before? Yeah. When you break the glow stick, is that an exothermic reaction or endothermic reaction? If you have a glow stick, the glow stick actually is not hot. If you break a glow stick, it's not hot. But still is an exothermic reaction because light is also an energy. It releases energy in form of light. Alright, so far so good. Hopefully you got this down. Now, I have some 1A reminder. These are the stuff that you should have learned in Chem 1A, but I'm going to briefly go over some of them. One of the 1A reminders that I want you to go back and review on your own is Hess's Law. Hess's Law was a way to figure out delta H of the reaction based on known delta H's, right? So you have a reaction and you don't know the delta H. Based on the other reactions that we do know that delta H is, we can figure this one out. The second one was heat of formation. And I'm going to go over it right now to review Chem 1A with you a little bit, because you have to know this before we can do this part of the chapter. So delta H of the formation, if you remember, that was delta H of formation. What delta H of the formation is a change, and when I make sure that it's a change in enthalpy to make something from its pure element. Change in enthalpy. And enthalpy is basically a fancy word of saying heat. So delta H, if you want to sound fancy and impress someone, do this. Instead of saying delta H, say, oh, change in enthalpy. I'm completely kidding about that. Usually people don't get impressed when I talk chemistry. So far, so good. So that means, how can I make something from its pure element? So how can I make something from its pure element? So far, so good. Okay, so let's do an example. Let's say I have calcium carbonate, right? How would I make calcium carbonate? I would take calcium, that's how it exists in nature, and carbon, how it exists in nature, and I would take O2, that's how it exists in nature, and I would form calcium carbonate. Again, how you make things from its pure element. This is how it exists in nature, how it exists in nature, how it exists in nature. How I made this from its pure element. That's what I mean. Okay. So delta H of formation for calcium carbonate is negative 1207 kilojoules per mole. Again, delta H of formation is how you made something from its pure element. So if I want calcium carbonate, pure element is calcium, pure element is carbon, pure element is oxygen. How I made that from what nature has given me. That's delta H of formation. And this is the delta H of the formation. Now, if you look at this delta H of the formation, a couple things to remind you from what you learned in Chem 1A. This is a negative value. What does that mean? That means it is exothermic reaction. Now remember, if you have an exothermic reaction, that is favored. Because not only you didn't require energy, net, you actually released energy to the surrounding. So it's favored. And what this is showing me that the compound that I made is more stable than its pure element. It's pretty stable. I can do that. Alright, now in Chem 1A, you learn that to figure out the delta H of formation, in Chem 1A, you figure out that to determine delta H of the reaction is product minus reactant, and you use the delta H of the formation for product and you subtract it from the reactant. Okay, again, this is a little bit review from what we talked about in Chem 1A. So Hesss Law, heat of the formation, those are the two things you have to know. Now, let's do a practice problem to make sure everyone is on the same page. Let's say I have 2 C2H2 gas plus 5 O2 gas goes to 4 carbon dioxide gas plus 2 H2O. This is liquid. This is a combustion reaction, right? Combustion reaction. I'm going to give you the delta H of the formation for each compound in kilojoules per mole. Okay? This 2 is driving me crazy. It's too far away. There we go. I'm going to give you the delta H of the formation, basically how much energy change we had how much energy we need or we require or we release to make these from its nature elemental form, from its pure form. Delta H of the formation of C2H2 is 227. Carbon dioxide is minus 394. And water is negative 285. Okay. Again, I looked up those values. I looked up the delta H of the formation for each one. You follow me so far? Okay. Now for oxygen, I'm not going to look up the delta H of the formation for oxygen. I want you to tell me what is the delta H of the formation for oxygen. Hopefully you're yelling right now that, hey, the delta H of the formation for oxygen is 0. And that is correct. Why? Because do you need to make O2? No, that's how it exists in nature. So you don't need to make it, because delta H of the formation is a change in enthalpy to make something from its pure element, like calcium carbonate. Now this is a pure element. I don't need to make it. So the delta H of the formation is 0. Now, for this problem, what I want you to do, I want you to figure out the delta H of the reaction. What we talked about a minute ago, the way you do this is product minus reactant. Hopefully, this is a review for Chem 1A. Let's do this together still. Product minus reactant. So to figure out the delta H of the reaction, you use delta H of the formation and you go product minus reactant. Okay. What is my product? Carbon dioxide, negative 394 is kilojoules per mole. Okay. Now it's kilojoules per mole. So mole does matter. So you have to be careful about the coefficient, because the coefficient of the mole ratio. How much do I have? I have 4 of those. So you have to multiply it by the moles, which I have 4 mole. So the mole can cancel out. I'm going to add up all the product together, and I'm going to add up all the reactant. Then is water, negative 285, again kilojoules per mole, but you have to multiply it by the coefficient because it's kilojoules per mole. So you have to consider how many of that do you have. Again, what I'm getting, these numbers are right here, and the coefficients matter. Okay, so these are all my product. These are all my product minus. So I add up all my product now minus my reactant. My reactant, what do I have? I have 227, again, kilojoules per mole. So what do I have to do? Multiply by mole, which is 2 moles. So this can cancel out. Plus oxygen is 0. So I don't have to worry about it. So product minus reactant, but you have to care about the coefficient because you have to cancel out the number of moles. Now, if I do this, what I end up getting negative 2600 kilojoules. Make sure you have the math down. So far, so good. Okay. So again, delta H of the formation. If you have delta H of the formation, you can figure out the delta H of the reaction by product minus reactant. Okay. Now, I want to talk about this delta H. And again, hopefully in Chem 1 you got this down. But I want to make sure everyone is on the same page. I want to talk about the delta H of the reaction. So we said delta H of the reaction is change of enthalpy. Okay. Let's take a step back. So you know what's the delta H of the formation, how much I need to make something from its elemental form, from pure form. You can figure out the delta H of the reaction by using the formation, right? Product minus reactant. Now, what does this delta H of formation mean? Delta H is change of enthalpy. That's what but what does it really mean? Here's one way to look at it, okay? Let's say you are going to demolish and build a house. and that's going to cost you $200,000. Then you are going to sell the house for $450,000. What is your net profit? You demolish and you build a house for $200K and you sold the house for $450K. What is your net profit? Your net profit is $250,000. That's your net profit. That's exactly the way to look at delta H of the delta H of the reaction. Is going to cost energy to break bonds. It costs of money to demolish and build a house. You are going to gain energy when you make bonds. You made some money when you sold the house. Delta H is your net profit. How much it costs to break the bonds. How much energy did I gain to make those bonds? Making bonds, you gain energy. Breaking bonds is going to cost you energy to break those bonds. Delta H is your net profit. Delta H is your net profit. So far, so good? Okay. So, we said, know the Hesss Law, know the delta H of the formation. And so these are the two things we talked about. Now, here's the third one we're going to talk about. We're going to talk about bond energies. Again, hopefully this is all review from Chem 1A, but if it's not, it's okay. Or bond enthalpy. Okay. You're going to do bond energies or bond enthalpies. Now, I have emailed you guys a handout. Take out that handout. Here is a handout. Now, here is bond energies. Here's a table with all the bond energies. Okay? Remember, we require energy to break a bond. We require energy to break a bond. And then you are going to gain energy when you make a bond. Okay? And that's another way to estimate the delta H of the reaction. So that's another way to estimate the delta H of the reaction. Okay. Now, if you look at this chart, I want you to look at a couple things that are interesting. And then that's one here. Double bond, triple bond versus a single bond. No surprises there, right? The triple bond is stronger than a double bond. So if a triple bond is stronger than a double bond, you're going to need more energy to break it. Okay. Now, if you look at it, all these energies are positive. All these energies are positive because we need energy to break the bond. So these are endothermic. Now, if you want to make the bond, what do you have to do? Just make these energies to be negative. Okay? Because these are energies that we need to break the bond. If you want to make that bond, the values would just be negative. Okay? So far, so good. Now, let's do a practice problem together right now. What I'm going to draw a molecule for us to figure out the delta H of the reaction. We can estimate the delta H of the reaction using bond enthalpy. Plus F going F2 goes to, okay, double bond and then C. All right. Now, let's do this together. And there is an there is an F, and then H and H. Okay? Now, to figure out, using bond energies or bond enthalpies, to figure out delta H of the reaction, here's what you have to do. You have to do broken minus made. Broken minus made to figure out, to estimate the delta H of the reaction. I'm going to go over this one more time because I want to make sure you really understand this. So here is bond energies that I've given you. This is another way to figure out and to estimate the delta H of the reaction. We said it's going to cost me energy to break the bond. I'm going to gain some energy when I make the bonds. So is going to be hard. I'm going to need energy to break the bond because I require energy. I require energy to break the bond. When you require energy, then the energy has to be positive. So I would just take these numbers. But when I make the bond, you release energy. You release energy to make the bond. That's why it will be minus made. So broken minus made, because these numbers would have to be negative when you make it. Because remember, when we make it is good. You gain energy. You release energy to the surrounding. But when you break it, it costs you energy. You require energy to break it. Require energy to break the bond, but you gain some energy. You release energy to make the bond. And this is why it's broken minus made, because when you release energy, it's going to be a negative value. Okay, now let's come over here. So you have that in front of you. Now here what we're going to do, you want to look at broken versus made. What is broken? Okay, tell me. What is broken? A double bond is broken. What is broken? The F2 bond is broken. What is made? I make 2 CF bond and I make 1 carbon-carbon single bond. So again, it's broken minus made, and you have this chart right over here. So let's do this together. My broken is going to be, you can even do it on the chart, and then you can check your answer. 614 plus 155, that's going to be my broken, minus my made is 348 plus 485 times 2. I'm going to double check that number. I'm going to check that CF is that number. So let's find CF, yeah, 485. Perfect. And I have 2 of them. Again, by having broken minus made. By having this minus here, you're making these values to be negative, because when you make something is good, you're releasing energy to the surrounding. What I get is negative 549 kilojoules of energy. Now, what can you tell me about this reaction? This reaction overall is exothermic. This reaction overall is exothermic. Okay, so far so good. All right, so this was a little bit review from Chem 1A that I wanted you to have, and the next time we start doing things more from Chem 1B. So remember, Hess's Law, I need you to review that on your own. That was when you don't know the delta H of a reaction, but there are other reactions that you know the delta H's. You can use those to figure it out. Heat of the formation, I went over that in detail. Basically, you can use the delta H of the formation to figure out the delta H of the reaction. It's product minus reactant. Okay? And we said every time you have a negative delta H of the reaction, that's favored. Product minus reactant, we did a practice problem. This is easy. Just don't forget that you have to multiply it by the coefficient. And then we said that another way to figure out the delta H of the reaction and to estimate it is you can the bond energy, broken minus made. And I want you to remember, it requires energy to break the bond, but you release energy to make the bond. That's why we make the number to be negative, because you release energy. That's favored. Okay, nice job. And then next time we'll start talking about more about delta H of the reaction and how you can predict if a reaction is going to happen or not happen.